So I'm a seismologist. The two basic problems, one is studying Earth structure, trying to relate it to, say, plate tectonics or geodynamics or the dynamics of continents. The other is trying to understand the earthquakes themselves and perhaps ultimately to predict them. So those are really two basic problems that as seismologists we do address, and I'm interested in both of these. So a seismometer is most simply a mass on a spring. So when the Earth is disturbed, it starts moving, this mass starts moving up and down. And there's a lot of complexity that goes into this, but effectively that's what you're measuring. And so we have a record of wave propagation through the Earth recorded at many stations, and there are thousands of stations throughout the world. And we use that, again, both to image the structure of the Earth, but we also use it to try to understand how the earthquake ruptured, how deep it was, where it was, for example. So all the characteristics of the earthquake that we would like to understand, we can get from these seismic waves. Seismographs are measuring seismic waves that are passing by. A strain meter measures something very different that you can only see when you're close up to the earthquake, and that is the slow deformation that takes place as an earthquake occurs, or even slow deformation unrelated to earthquakes. And the way it works is, at least the one that is designed here, is essentially a sack of fluid in a cylindrical instrument that is then squeezed, and as it's squeezed it changes the volume of the fluid, and you can measure that change in volume very, very accurately to 1 part in a billion. So it's a very, very, very precise measurement, and it's measuring something, again, that seismographs cannot measure. The slow deformation, the slow strain. And there are various natural laboratories that people have used to study earthquakes. There's one in California called Parkfield. This is a town of 19 people, but happens to sit on the San Andreas Faults, right between LA and San Francisco. And it's a place where every 20, 25 years or so there's a magnitude 6 earthquake. It doesn't hurt very many people or anything, but it's fairly regular. So we've put a lot of instrumentation there to try to catch possible precursor, to try to just study in general the earthquake problem and the earthquake cycle through this 20, 25 or so years. Another one is up in Cascadia. So this is sort of Washington, the west coast of Washington. In this case, there are slow earthquakes that occur roughly every 14 months. It's a relatively new phenomenon. This has been known for maybe the last 5 or 6 years. And there's one of these slow earthquakes takes about 10 days, and then every 14 months you get another one, and so on. So something like this allows us to study these phenomena almost like a natural laboratory. So the closest we come to actually doing laboratory or controlled experiments. It's not an oxymoron in the sense that if you think of an earthquake as what we call stick-slip, so you build up stress on a fault and then it slips rapidly, and that rapidly is corresponding to it scales with the velocity of seismic waves. Okay. That same fault, what if same process, stick-slip, but let's say it took 2 days instead of 10 seconds for the slip to take place. Now, it probably would not generate any seismic waves at all because it needs to go quickly for that to happen. Nevertheless, it's a very similar phenomenon. Again, it's still stick-slip. It's not continuous motion for the motion between the plates, but it's rapid motion, but slower than what we would call a normal earthquake. Well, the issue of understanding earthquakes is one that has been with us for a long, long time. I think that is ripe for a breakthrough for a couple of reasons. One is observationally, there's been, and Carnegie's actually been heavily involved in this, there's been a big jump in the deployment of instrumentation, both strain meters, GPS receivers, to study the slow deformation problem much more systematically than we ever have before. So there's more instrumentation available. There are new phenomena being discovered sort of as a result of this. These slow earthquakes I told you about in Washington. This, I think, is an indicator of a whole spectrum of behaviors that if we understand them, of this slow earthquake variety, I think we may be able to ultimately predict earthquakes. So another area that I think is ripe for dramatic development, and one that I've become very interested in, has to do with plate tectonics. It's something that is, many people maybe think that plate tectonics is a solved problem and there's nothing more to do. But in fact, there are two aspects of plate tectonics, and their interaction really hasn't been really addressed very well in my mind. And that is, the normal plate tectonics we know about, and then this concept called the Wilson cycle. And the Wilson cycle is the cycle of continental breakup and continental collision. So there's sort of normal plate tectonics. There's this Wilson cycle of continental breakup and continental collision, which really that's what makes ocean basins. That's what makes mountain building episodes. The interaction between those two is potentially very important, and it's something we've been pursuing to the point that it may actually shut off plate tectonics altogether. It's something that I've been very interested in. And so the evaluating and understanding the Wilson cycle, I think, is something that is there's a need to develop this much more fully than it has in the past, because of its potential impact on the evolution of the Earth over the last 4 billion years or so. So that's another area that I think there's. I mean, the evolution of the Earth in general is still a very important problem. But this specific part of it, understanding how the Wilson cycle plays into this evolution, I think is something that deserves a lot of attention. It's something I'm going to give a lot of attention to.